something is amiss in our comprehension of the universe. Cosmology is, by all accounts, heading for a confrontation on one of its most essential inquiries. How quick is the universe expanding? For more than a decade, two kinds of estimations have been in conflict. Perceptions of the current universe regularly find the rate of extension, called the Hubble constant, to be around 9% quicker than forecasts based on early universe data. Specialists trusted that the James Webb Space Telescope, the most advanced telescope ever built, would help settle the inquiry once and for all. However, consensus has so far failed to appear. Rather, the Space Observatory has solidified the inconsistency with incredibly exact, groundbreaking perceptions that threaten to affix the standard model of cosmology. The new physics expected to alter or even replace the 40-year-old hypothesis is now a subject of debate. An astonishing and intriguing possibility is that there's something we do not yet comprehend about the universe. Join us as we dive deep into how new ultra-deep pictures from James Webb just confirmed that there is something truly amiss with our understanding of the universe. Our universe began with a bang, the Big Bang. Energy, mass, and space streaked into reality, all within a momentary moment. Then, the youthful universe was formed. A growing, roaring plasma stock of matter and antimatter particles that jumped into reality just to obliterate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other altogether. Yet researchers believe that some unexplored world irregularity empowered more matter than antimatter to be produced, saving the universe from prompt implosion. Gravity compacted the plasma pockets, pressing and warming the matter so that sound waves traveling just over around 50% of the speed of light, called baryon acoustic oscillations, undulated across their surface. In the meantime, the high-energy density of the early universe's packed contents expanded spacetime. A little part of this matter safely survived the fry as the universe expanded like an inflatable. The standard story goes that ordinary matter, which interacts with light, solidified around clusters of invisible dark matter to make the first worlds, connected together by a tremendous, infinite web. Initially, as the universe's substance spread out, its energy density and consequently its extension rate diminished. However, about 5 billion years ago, galaxies began to subside once more at a consistently quicker rate. The reason was another undetectable and strange substance known as dark energy. The simplest and most well-known explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the extending fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe developed, its general matter density dropped, while the dark energy density remained the same, progressively making the latter the greatest supporter of its overall extension. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's extension. They are also key ingredients in the lambda cold dark matter, Lambda CDM model of cosmology, which maps the evolution of the universe and predicts its end, with matter eventually spreading so far that it encounters a thermal death called the Big Freeze. Many of the model's predictions have been demonstrated to be highly accurate. However, here's where the issues start. Regardless of much looking, space experts do not know what dark matter or dark energy are. As Offrail, Professor Love, a professor of astronomy at University College London who is engaged in world studies of dark energy, said, "A great many people agree that the universe's present composition is 5% ordinary nuclear matter, 25% cold dark matter, and 70% dark energy. The humiliating truth is we don't comprehend the last two of them yet. An even greater threat to the Lambda CDM model has appeared. Depending on what technique astrophysicists use, the universe seems to be expanding at different rates, a discrepancy known as the Hubble tension. Techniques that peer into the early universe show it expanding significantly quicker than Lambda CDM predicts. Those methods have been checked and confirmed by innumerable perceptions. As a result, Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb estimation, said, "The only reason I can understand for them to differ is that maybe the model we have between them is missing something. Estimating the universe's extension takes a bit more than a radar gun." The principal method to measure this development looks at the so-called cosmic microwave background, CMB, a remnant of the universe's first light produced just 380,000 years after the Big Bang. The imprint should be visible across the whole sky, and it was planned to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this astronomical baby picture, the universe is mostly uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it cluster as the universe detonated outward. This soap bubble structure swelled into the cosmic web, an organization of jumbling strands along whose convergences galaxies would be formed. By concentrating on these waves, cosmologists deduced the amounts of ordinary matter and dark matter and a value for the cosmological constant or dark energy, resulting in a standard model that disagreed with a Hubble constant of about 67 kilometers per second per megaparsec. We should stop on this number for a moment. If a galaxy is a distance of 1 megaparsec away from us, that means it will retreat from us and we from it at 67 kilometers per second. At 20 megaparsecs, this downturn grows to 1,340 kilometers per second and continues to increase dramatically from that point forward. If a galaxy is any farther than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second technique to find this development rate utilizes pulsating stars called Cepheid variables, dying stars with helium gas outer layers that expand and contract as they absorb and release the star's radiation, making them intermittently glow like distant signal lights. In 1912, cosmologist Henrietta Swan Leavitt found that the brighter a Cepheid is, the slower it will pulse, empowering cosmologists to gauge a star's absolute brightness and hence check its distance. It was a milestone discovery that turned Cepheids into abundant standard candles to measure the universe's massive scale. By hanging observations of pulsating Cepheids together, space experts can build infinite distance ladders, with each rung taking them a step further back into the past. It's one of the most reliable methods that space experts have today for measuring distances. To construct a distance ladder, astronomers build the first rung by picking nearby Cepheids and cross-checking their distance based on pulsating light. To that found by Math Wendy Fredman, an astrophysicist at the University of Chicago, stated the following rungs are added utilizing Cepheid readings alone. Then, space experts look at the distances of the stars and supernovae on each crosspiece and analyze how much their light has been redshifted, stretched to longer, redder frequencies as the universe extends. This gives an exact estimation of the Hubble constant. In 2019, the technique was used by Rees and his teammates, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was unstable, an unthinkably high development pace of 74 kilometers per second per megaparsec, when contrasted with the Planck estimation. However, Hubble missed the mark on fundamental accuracy for the crowded regions of space the group was studying, causing some distant Cepheids to obscure into adjoining stars. Disagreeing cosmologists had some room left to argue that the result, while stunning, might have come from a measurement error. So, when James Webb launched in December 2021, it was poised to either determine the error or cement it. At 6.5 m wide, its mirror is just over 3 times the size of Hubble's, which is only 2.4 m wide. Not only can James Webb detect objects multiple times fainter than Hubble can, but it is also undeniably more sensitive in the infrared range, enabling it to find in a wider scope of frequencies. By contrasting Cepheids measured by James Webb in the galaxy NGC 4258 with bright type Ia supernovae, another standard candle, since they all explode at the same absolute brightness in distant galaxies, Rees and his partners arrived at an almost identical outcome, 73 kilometers per second per megaparsec. Different estimations, including one made by Fredman with the Hubble Space Telescope on the rapid light of the most luminous tip of the branch red giant stars, and another with light bent by the gravity of massive galaxies, returned with particular outcomes of 69.6 and 66.6 kilometers per second per megaparsec. A different result utilizing the bending of light also yielded a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling, as indicated by Ronan Kai, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension. The CMB temperature is measured at the level of 1% accuracy and the Cepheid distance ladder estimation is approaching 1%, so a contrast of 7 kilometers per second, while not especially large, is incredibly unlikely to be a random opportunity. There is a significant implication. To explain the new outcome leaves the response wide open, splitting cosmology into groups pursuing vastly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 meeting at the Kavli Institute for Theoretical Physics in California led to multiple potential solutions that have since become prominent, many offering distinctly unique understandings of what the universe truly looks like. One of them suggests that dark energy might not be so constant after all. For example, there's a possible scenario in which dark energy's intensity would decrease over time. Another explanation involves a new dimension of spacetime called the fifth dimension, which, in theory, could cause a difference in the calculation of the Hubble constant. Whether one of these would fully explain this discrepancy remains a highly speculative possibility. What the latest findings suggest is that we may have to rethink and revise fundamental assumptions regarding the universe's expansion. The James Webb results, which seem poised to have profound consequences, could challenge one of the most central tenets of modern cosmology. The universe is far more complicated than the current models suggest. Time will tell whether these latest discrepancies lead to a transformative breakthrough or simply indicate that the tools and theories we've relied on so far need fine-tuning. For now, one thing is clear: our comprehension of the universe's evolution is still very much a work in progress. The profound implications of the latest discoveries are still unfolding. The James Webb Space Telescope, by delivering unprecedented accuracy, has presented cosmologists with a new frontier. As researchers continue to refine their methods, the data may either reinforce the Lambda CDM model or push us toward entirely new theories. A central question remains: can we fully trust the methods we've been using for decades? Or are there aspects of the universe that we have yet to comprehend? The new findings, by creating significant contradictions in our predictions, suggest that something fundamental might be missing from the puzzle. Dark matter and dark energy, once considered largely mysterious but manageable in the Lambda CDM framework, now stand at the center of this growing uncertainty. They were proposed to explain cosmic phenomena that could not be otherwise accounted for, like the bending of light around galaxies or the acceleration of the universe's expansion. Yet, as measurements become more precise, the models that rely on them are showing signs of strain. One possibility that has been suggested is that dark energy could be more dynamic than previously thought, evolving over time rather than being a constant force. Some cosmologists speculate that dark energy may change as the universe continues to expand, leading to variations in the Hubble constant that we are only now beginning to detect. If true, this would fundamentally alter our understanding of both the cosmos and its fate. Alternatively, new theories about spacetime are gaining traction. For instance, the notion of extra dimensions, dimensions beyond the familiar 3 of space and 1 of time, might be the key to explaining the Hubble tension. In this scenario, the fabric of the universe could behave in ways that defy our conventional understanding, leading to discrepancies in the observed rate of expansion. Other proposals look at the potential for new kinds of particles or forces that could affect the universe's expansion, even in ways that were not considered by the standard model. These could involve interactions between known particles or even unknown forces that could shift the cosmic balance in subtle but measurable ways. Such ideas are still in their infancy, but they open up the tantalizing possibility that the Hubble tension is the first indicator of a much larger revelation about the nature of the universe. Another avenue of research involves revisiting the early moments of the universe. The cosmic microwave background, CMB, provides a snapshot of the universe as it was roughly 380,000 years after the Big Bang. The detailed study of this ancient light has given rise to the Lambda CDM model. But what if new findings in the CMB, or in observations made by Webb in even more distant regions of space, suggest that the very assumptions we've made about the early universe are flawed? Could the conditions shortly after the Big Bang have been different than we've believed? These are questions that will require years of study, but the stakes could not be higher. The uncertainties at the heart of the Hubble tension are not just academic. They have the potential to reshape the entire framework of cosmology. They might even lead to an entirely new understanding of the cosmos that accounts for both the observed facts and the troubling discrepancies that have emerged. This could mean revising our most fundamental laws of physics, the very laws that govern the largest structures in the universe down to the smallest particles. Yet, cosmology is nothing if not a science of patience and precision. It is a field built on the careful accumulation of evidence, and the discrepancy between current observations and the Lambda CDM model may be resolved with more time, more data, and more advanced instruments. The James Webb Space Telescope has provided a massive leap forward, but it is only one piece in the larger puzzle. As researchers around the world continue to examine these new results, there is a growing sense that we are on the cusp of something profound. The next few years, with upcoming observations and continued study, will likely be crucial in determining the fate of the Hubble constant and the future direction of cosmology. Whether the answer lies in an unanticipated discovery about dark energy, new dimensions of spacetime, or even a radical rethinking of the Big Bang itself, one thing is certain. The quest to understand the universe is far from over. In the end, the true nature of the cosmos may be even more mysterious and complicated than we ever imagined. The universe might still have many secrets to reveal, and our current models, however sophisticated, could just be the beginning of an ever-evolving understanding of the grand, expansive universe we inhabit.